Hello friends, I am Dr. Gaurav. In this video, I will discuss about application of steady flow energy equation. Contents are mass and energy balance equation for steady flow process, nozzle and diffuser, turbine including steam or gas turbine and hydraulic turbine, compressor, centrifugal pump, throttling valve, adiabatic mixing, boiler and condenser. First is mass and energy balance in steady flow process. The mass balance for journal steady flow system is given as sum of all the mass flow rate entering the system or control volume is equal to sum of all the mass flow rate leaving the control volume. You can see in the diagram there is only one point of entry and one point of exit. So if we apply mass balance, we will get m over dot 1 equal to m over dot 2, that is mass entry equal to mass leaving. We can represent this mass flow rate as rho a c, where rho represent density, a represent area and c represent velocity. The rate form of journal energy balance for steady flow is given as rate of energy entering the system equal to rate of energy leaving the system. So here Q represent amount of heat given to the system. Here W represent amount of work done on the system. So this is the rate of heat and this is the rate of work done on the system, plus summation of energy associated with the flow stream at the entry points. M over dot represent mass flow rate, U represent internal energy per unit mass as it is a small u, plus P into V represent flow energy per unit mass, where P is the pressure, small v is the specific volume, C square upon 2 represent kinetic energy per unit mass, plus Gz represent potential energy per unit mass, where C represent velocity, Z represent elevation, G represent acceleration due to gravity. So this is for the entry point, left side of the equation. Right side represent the exit or leaving. So this Q over dot out means amount of heat given by the system. W over dot out means work rate of work done by the system, plus this is the energy associated with the flow stream. The next equation is same, only we have replaced this U plus PV with the small h, it is specific enthalpy. If we apply this energy balance for the given diagram, then we will get this equation. As there is only one entry point, so here we have replaced this summation with one symbol, and there is only one leaving, so we have replaced this summation with the two symbol. Next is symbol used. Capital C represent velocity in meter per second, Z represent elevation in meter, small g represent acceleration due to gravity in meter per second square, m over dot represent mass flow rate kg per second, p represent pressure in Newton per meter square, v represent volume in meter cube, W over dot represent rate of work done in watt, Q over dot represent rate of heat transfer in watt, U represent internal energy in joule, capital H represent enthalpy in joule, PV represent flow energy or flow work in joule, where P is the pressure and capital V is the volume, Ke represent kinetic energy in joule, Pe represent potential energy in joule. Symbol per unit mass. Small v represents specific volume in meter cube per kg. Small w represents work done per unit mass in joule per kg. Small q represents heat transfer per unit mass in joule per kg. Small u represents internal energy per unit mass in joule per kg. Small h represents specific enthalpy in joule per kg. P into small v, where P is the pressure, small v is the specific volume, represent flow energy or flow work per unit mass in joule per kg. C square upon 2 or small ke represent kinetic energy per unit mass in joule per kg. Gz or small p represent potential energy per unit mass in joule per kg. Next is nozzle and diffuser. Nozzles and diffusers are commonly utilized in jet engines, rockets, spacecraft, and even garden hoses. Nozzle is a device that increases the velocity of fluid at the expense of pressure. A diffuser is a device that increases the pressure of a fluid by slowing it down. Thus, nozzle and diffuser perform opposite tasks. As you can see in the first diagram is about nozzle. So, V1 is the velocity entering and V2 is the velocity leaving. So this V2 will be very large as compared to V1. This is the purpose of nozzle, to increase the velocity. In the second diagram we are having diffuser. As you can see, the shape of both nozzle and diffuser are just opposite. V1 is the velocity entering and V2 is the velocity leaving. V2 is very less as compared to V1, because here our main purpose is to increase the pressure. Characteristics of nozzle and diffuser. The wall of nozzles and diffuser are insulated. That is, heat flow rate will be zero. That means this quantity and this quantity will be zero. Nozzle and diffuser typically involve no work. That is, W over dot will be zero. So here we have to eliminate this W over dot in and W over dot out. Next is nozzle and diffuser are horizontal, that is no elevation difference between inlet and exit, that is Z1 equal to Z2, or we can say change in potential energy equal to 0. So this term will also be eliminated, this GZ term. Kinetic energy change must be accounted for analyzing the flow through these devices. So we have to count the kinetic energy change. So what left after eliminating Q over dot, W over dot and GZ? This term will left. If we are having only one entry and one exit, then we can write down left side is representing the entry point and right side represent the exit point. If we apply the mass balance for the given figure, as we are having only one entry, one exit, so we can say mass flow rate entering equal to mass flow rate leaving. And if we assume these two mass equal to m over dot, then we can put this in the above equation. We will get this one. As m over dot is common, it will be cancel out. So what left? H1 plus C1 square upon 2 equal to H2 plus C2 square upon 2. So this is the energy balance equation in case of nozzle and diffuser. If enthalpy is in kilojoule per kg and kinetic energy is in joule per kg, if this H is in kilojoule and this H is in kilojoule per kg and C1 square upon 2 is kinetic energy per unit mass is joule per kg, then we have to convert this into kilojoule. How will we convert? You have to divide this by 1000. So we will get this equation. We have divided this by 1000. If you find the value of C2, it comes out to 200 into H1 minus H2 plus C1 square whole under root. If in nozzle we consider initial velocity is negligible as compared to exit velocity, then we can eliminate this term C1 square. So we will get this equation. if you take 2000 out of this under root, the final equation will be C2 will be equal to 44.72 whole under root H1 minus H2 in meter per second. But you have to remember one thing, that is H is given in kilojoule per kg and kinetic energy is in joule per kg. Then you will get this equation in meter per second. The cross-sectional area of nozzle decrease in the flow direction for subsonic flow. So you can see this is the diagram of nozzle, and from the starting point up to this minimum area is known as throat. So up to this we are having subsonic velocity. So you can see the area is decreasing. At the throat the velocity is sonic, that is equal to sound velocity in that particular medium. So at the throat, that is at minimum area portion, we will have sonic velocity. And if you want to further increase the velocity more than that of the solid sonic velocity, that is sound velocity in that particular medium, then you have to increase this area. So in this increased area you will get the supersonic flow. The reverse is true for diffuser. Next is turbine, compressor and pump. In this we will consider centrifugal pump. In steam, gas or hydraulic power plants, the device that drives the electric generator is the turbine. As the fluid passes through the turbine, work is done against the blades which are attached to the shaft. As a result, the shaft rotates and the turbine produces work. Compressor as well as pump and fans are devices used to increase the pressure of a fluid. Work is supplied to these devices from external source through a rotating shaft. Therefore, compressor involve work input. So in compressor we are supplying the work, and from turbine we are getting the work as the output. Even though these three devices function similarly, they do differ in the task they perform. A fan increases the pressure of a gas slightly and is mainly used to mobilize a gas. A compressor is capable of compressing the gas to very high pressure. Pumps work very much like compressor except that they handle liquid instead of gases. So in compressor we use gases, in case of pump we use liquid like water. Characteristic of steam or gas turbine. A steam or gas turbine is a device for obtaining work from a flow of fluid expanding from high pressure to low pressure. Turbine is a work producing device, that is W over dot in will be equal to 0, that is rate of work done on the system will be 0 as turbine produces the work. So in energy balance equation take this W over dot in equal to 0. Heat transfer from turbine is usually negligible since they are typically well insulated, that is amount of rate of heat transfer equal to 0. So this Q in 2 over dot in and Q over dot out will be 0. Potential and kinetic energy changes are negligible. That means this C square upon 2 plus GZ on the left side and on the right side C square upon 2 plus GZ will be eliminated as the changing in potential and kinetic energy is negligible. So if you apply all these conditions we will get this equation: m over dot 1 H1 is equal to m over dot 2 H2 plus W over dot out. As you can see, this is the diagram of a turbine. This side is smaller, this side is bigger. It means there is the expansion of fluid. So we are having only one entry, one exit, and we are getting work from the turbine. So we will get this equation. This is the equation in case of steam or gas turbine. m over dot 1, h1 equal to m over dot 2, h2 when 1 represent entry, 2 represent exit, plus w over dot out. If you apply the mass balance, you will get mass entering equal to mass leaving, and if we consider rate of mass entering equal to mass of rate of mass leaving equal to m over dot m over dot, then we can write down above equation in this way. So w over dot out will be equal to m over dot into h1 minus h2. This will be in kilowatt. So we can replace this w over dot out in terms of mass flow rate as m over dot w out, small w out. Small w out means work done per unit mass. So this m over dot will be cancel out. So we'll get w out equal to h1 minus h2 having unit kilojoule per kg. So if we replace this out with the turbine work, we will get this equation. And if we talk about the ideal gas, we know that for an ideal gas, change in enthalpy equal to Cp T1 minus T2. So this equation is valid particularly for ideal gas. Next is characteristics of hydraulic turbine. A hydraulic turbine or water turbine is a device which takes in water from a height. The water enters into the turbine. A part of its potential energy is converted into useful work, that is shaft work, which is used to generate electric power in a generator. Turbine is a work producing device. So W over dot in will be equal to 0. So in energy balance you have to put this W over dot in equal to 0. As there is negligible change in temperature of water, so this rate of heat transfer will be equal to 0. So Q over dot in and Q over dot out will be 0. And change in specific internal energy is 0, because we know that internal energy is a function of temperature. When the temperature is 0, so the change in internal energy will also be equal to 0. So this you have to eliminate this small u from left hand side and small u from the right hand side. As water is an incompressible fluid, its specific volume and hence density will remain constant. So we know that water is incompressible fluid, it means its specific volume as well as density will remain constant. So this small v1 equal to small v2, and we have assumed these two value equal to small v. So if you apply above condition on the energy balance equation, you will get this equation, as we are having only one entry and one exit. So you get this equation. If you apply mass balance for one entry and one exit, you will get rate of mass entering equal to rate of mass leaving equal to m over dot. So you can find out the value of W over dot out. Now, if you look at the given figure, from given figure, we have assumed this as the datum or reference line. So, the value of Z2 will be equal to 0 and we are having only Z1. So, if you apply this condition on W over dot out equation, you will get this as the equation. Now, we can replace this W over dot T with M over dot into small Wt. This m over dot is common, it will be cancelled out. So finally you get small Wt equal to V into P1 minus P2 plus C1 square minus C2 square upon 2 plus GZ1 in joule per kg. So this is the diagram of a hydraulic turbine. As water is coming from the certain height, it will rotate the water turbine, so it will produce the work, because if rotating shaft, it will produce the electricity from the generator. Next is characteristics of compressor. Compressor is a work absorbing device. That means in this case W over dot out, rate of work done by the system, will be equal to 0. So in the energy balance equation you have to take this W over dot out equal to 0. Heat transfer from compressor is usually negligible since they are typically well insulated. So this Q over dot in and Q over dot out will be equal to 0. Potential and kinetic energy changes are negligible. That means this c square upon 2 on the left side and c square upon 2 on the right side will be cancelled out, and gz on the left side and gz on the right side will be cancelled out. So what left? You will get this equation. After applying above conditions, you will get W over dot in plus M over dot 1 H1 equal to M over dot 2 into H2. If you apply mass balance for one entry and one exit, you will get rate of mass entering equal to rate of mass leaving equal to M over dot. So if you replace this W over dot in with M over dot small w in, this M over dot is common on both the side, it will be cancelled out. You will get small w in equal to H2 minus H1 in kilojoule per kg. So in means it is for compressor WC. So you get H2 minus H1 equal to H2 minus H1, and the units are kilojoule per kg. We can replace this H2 minus H1 with Cp T2 minus T1, and this is valid only for ideal gas. For other than ideal gas, we have to write down always this equation H2 minus H1. This is the diagram of compressor. Entry point is of bigger size and leaving is small because we are compressing. We are supplying WC amount of work to the compressor. Next is characteristic of centrifugal pump. Centrifugal pump is a work absorbing device, that is W over dot out equal to 0. As there is negligible change in temperature of water, so rate of heat transfer equal to 0, and change in specific internal energy, that is del U equal to 0, because we are saying there is no change in temperature. When there is no change in temperature, it means the change in energy will be equal to 0. As water is an incompressible fluid, so its specific volume and density will remain constant, that is small v1 equal to small v2, or we can say small v1 equal to small v2 equal to v. Now this is the energy balance equation. If you apply above conditions, that is W over dot out equal to 0, Q over dot in equal to 0, Q over dot out equal to 0, U on left side and right side will be cancelled out as the changes are 0, and so we will get this equation W over dot in plus M over dot 1 P1 V1 plus C1 square upon 2 plus GZ1 is equal to M over dot 2 P2 V2 plus C2 square upon 2 plus GZ2, as we are having only one entry and one exit. For one entry and one exit, the mass balance equation gives us rate of mass entering is equal to rate of mass leaving equal to M over dot. So if you find out the value W over dot in, you will get this equation. You can replace this W over dot in with M over dot small w pump. M over dot is common, so it will be cancelled out. So you will get the equation of W pump. Now you can replace, we have replaced this V1 and V2 with small v. So the final equation is small w pump equal to small v into P2 minus P1 plus C2 square minus C1 square whole divided by 2 plus G into Z2 minus Z1, and the unit is joule per kg. So this is the diagram of centrifugal pump. through electric motor we are supplying W amount of work to the pump and it is extracting water from the low level, and because of this pump we are getting water at the high level. So we have to consider this as the reference line. So this is the Z1, this is the Z2. Next is throttling valve. Throttling valves are any kind of flow restricting devices that cause a significant pressure drop in the fluid. Examples are adjustable valves, capillary tubes, and porous plug. Capillary tubes you must have heard in case of domestic refrigerator and air conditioner. Unlike turbines, they produce a pressure drop without involving any work. The pressure drop in the fluid is often accompanied by a large drop in temperature, and for that reason throttling devices are commonly used in refrigeration and air conditioning applications. The magnitude of the temperature drop or sometimes the temperature rise during a throttling process is governed by a property called the Joule-Thomson coefficient. So first a figure diagram is an adjustable valve, B represent a porous plug, C represent a capillary tube. So this we are having one entry and one exit, and this is the restricted opening, means there is decrease in the diameter. Characteristic of throttling valve: no heat interaction as tube is thermally insulated, so rate of heat transfer is equal to 0. That means Q over dot in and Q over dot out will be 0. Throttling valve involves no work, that is W over dot 0. So W over dot in and W over dot out will be 0, and any change in potential energy is negligible. So we will have this Gz on the left side equal to Gz on the right side, so it will be cancelled out. Even though the exit velocity is often considerably higher than the inlet velocity, in many cases the pressure in the increase in kinetic energy is insignificant, that is change in kinetic equal to 0. So we will eliminate these terms, c square upon 2 on the left side and c square 2 upon the right side will be eliminated. So what left after applying all the conditions? M over dot 1 H1 equal to M over dot 2 H2. As there is only one entry and one exit, so mass flow rate entering equal to mass flow rate leaving equal to M over dot. So M over dot will be cancelled out. You will get H1 equal to H2. So this is the throttling condition. We can replace this H with U plus PV. So we will get U1 plus P1 small v1 is equal to U2 plus P2 small v2 equal to constant. Or we can say internal energy plus flow energy equal to constant. A throttling valve is sometimes called an isenthalpy device because enthalpy is constant. The temperature of an ideal gas does not change during a throttling process because we know that H is a function of temperature, and in this case the change in enthalpy is 0. That means we can replace this change in enthalpy with Cp T2 minus T1 only for ideal gas equal to 0. That means T2 will be equal to T1. This is valid only for ideal gas. So in throttling process, temperature entry and equal to temperature at exit only for the ideal gas. Next is adiabatic mixing. The mass balance for the given figure, you can see there are two entry and only one exit. So if we apply the mass balance equation, so rate of mass entering equal to rate of mass leaving. So m over dot 1 plus m over dot 2 is equal to m over dot 3. If we apply the energy balance, So you can see from the figure that heat transfer, work interaction and change in kinetic and potential energy is 0. So this Q over dot in and Q over dot out is 0. W over dot in, W over dot out is 0. And this changes in kinetic and potential energy is 0. It means C square upon 2 on the left side equal to C square upon 2 on the right side, so it will be cancelled out, and Gz on the left side equal to Gz on the right side, that is potential energy change is 0, so it will be cancelled out. So what left? We are having two entry, so m over dot 1 h1 plus m over dot 2 h2 equal to m over dot h3. Now we can replace this m over dot m3 with m over dot m1 plus m over dot m2. So we will get a relation m over dot m1 divided by m over dot m1 divided by m over dot 2 is equal to h3 minus h2 divided by h1 minus h3. Next is boiler. Boiler is the engineering device used for steam generation at constant pressure. The mass balance for the given figure, as we are having only one entry and one exit, so we will have m over dot 1 equal to m over dot 2, or we can assume these two mass equal to m over dot. Now this is the energy balance equation. If we apply the condition such as heat given out, work interaction and change in kinetic potential is equal to 0, that is Q over dot 0, W over dot in, W over dot out 0, and C2 square upon 2 equal to C2 square upon 2 on the right side and left side equal, it will be cancelled out. Gz on the left side and Gz on the right side will be equal, so it will be cancelled out. So what left? You will get Q over dot in plus M over dot into H1 is equal to M over dot H2. As we have assumed M over dot 1 equal to M over dot 2 equal to M over dot. So we can replace this Q over dot in with M over dot small q in. So we'll get small q in plus H1 equal to H2. As we are supplying the water in the boiler, and on the other hand W amount of heat is given to the water, due to which water is converted into steam. So we are having only one entry and one exit, and we are supplying Q amount of heat. Next is condenser. The condenser is used to condense the steam in case of steam power plant and condense the refrigerant vapor in the refrigeration system using water or air as cooling medium. So it is a heat exchanger. This is the energy balance equation. As you can see, the system insulated, it means Q over dot in and Q over dot out will be 0. Work interaction is also 0, as we are not supplying or getting any work. So W over dot in and W over dot out will be equal to 0, and change in kinetic and potential energy is 0. That means C square upon 2 on the left side is equal to C square upon 2 on the right side. It will be cancelled out. Gz on the left side and Gz on the right side will be cancelled out, as both values are equal. So we will get M over dot S, because at the entry we are having two entry, this entry and this one, and for the steam we have considered mass as M over dot S, and for the water we have considered the mass M over dot W. So M over dot S HS plus M over dot W HW1 is equal to M over dot S into HCO, CO means condensate out, plus M over dot W, because this mass flow rate will remain the same at the entry of water in and at the exit of water out, into HW2. If you take the M over dot S term common on one side, you will get this M over dot S HS minus HCO. is equal to m over dot w HW2 minus HW1. Now you can replace this HW1 minus HW2 minus HW1 with CPW TW2 minus TW1. TW2 is the temperature of water leaving the system. TW1 is the temperature of water entering the system. So we can say heat lost by steam is equal to heat gained by water. Thanks. Any questions you can write to me gaurav.citm@gmail.com.